Okay, good afternoon. Today we're going to hear a slightly different take on object-oriented programming, maybe a little more like what the rest of the world thinks, but not entirely like what the rest of the world thinks. This chart that Jordy is writing on the board actually is about where the rest of the world stands relative to what Engels is talking about. To help you understand the lecture, I've put up on the board here a translating dictionary between his names for things and our names for the same ideas. These three are actual things in the language. That's why they're in capitals. When he talks about a small integer, he doesn't mean 6 or 7. He means anything less than, absolute value less than 2 to the 31st. He's going to define a class point in Smalltalk. And these three boards are the equivalent definition of class point in the obj.scheme OOP language. So if you can leave these board lights on, not the tables, but the boards, while we're watching the video, thanks, that'd be great. Go.
I had the good fortune to participate in the Smalltalk project with Alan Kay and the other good people who worked on it. And it was an interesting project. We designed a programming language and then used it to build an operating system and a graphical user interface. And then built on top of that a whole programming environment consisting of editors, debuggers, compilers, and then used those to implement several large applications, such as a music system and an animation system. And then we had the opportunity to do something which most other projects don't get to do, which is when it was all built, instead of going commercial and delivering it, we got to throw it all away and do it over again the way we would have wanted to do it. And in the process, we got to find out about complexity because the applications were quite complex. And we had a chance to try out several solutions to dealing with that complexity. And when you try to break a complex problem down, you want to try to break it down into as few parts as you can, and you want them to be as independent as they can be. That just leaves you with a simpler analysis. And then if you have general parts that you've put together or that you have available, when you use them to put together a system, it will be easier to learn because there are fewer components. You can be more productive because the components are hopefully more general. And the systems you build will be more maintainable because, built with fewer components, you'll encounter less things you don't know about when you go in to maintain it. Now, if you look at the evolution of computer software systems over the last 40 years or so, you find that we started out with incredibly basic components that were not at all flexible, just the instructions of the machine and the memory cells available in it. Then on top of that, we put a more general layer with formulas for the instructions, a symbolic sort of description, and variables instead of simple memory cells. And then we added in the notion of procedures, which sort of made a much more flexible kit of things to work with, because now you could augment the basic set of instructions that were available. And then soon after that time, we also developed data structures, which again allowed you to define your own new memory primitives, as it were. And at each level, it became possible to break problems down more simply and more generally. Then, toward the end of the 60s, the beginning of the 70s, we discovered, as we tried to do more and more complicated things, we discovered further problems, for instance, the use of go-tos in procedural text that made things not be modular, and we ruled that out with structured programming principles. And also, in the area of data structures, people were using data structures in unclean ways, and we cleaned that up by the use of abstract data types, where you basically bundle the data with the procedures that work on it and hide the information behind. So this is where we were at the beginning of the 70s. And the problem is that one still encountered difficulties when building really complex systems. For instance, if you do a large simulation of a hospital or something like that, you'll have several different kinds of data in that simulation. For instance, in a hospital, you might have doctors, nurses, and patients. And in building data structures for this simulation, you'll presumably implement structures for things like queues. For instance, the queue of people waiting at a door. And some programming languages at that time required you to have a different kind of queue for every kind of thing you're going to put into it. Now, as soon as you get to a large simulation, that becomes impossibly difficult. Or in this example, you would have doctors, nurses, and patients all waiting at the elevator sometimes or at a door. So it requires the queue to be able to have all these different kinds of things in it. And there will be code like this scattered all over the system. Now, what you have to do then is inside of the queue, and this is even if the programming language allows you to do this, you'll have to have a test on what kind of thing is in the queue. For instance, if you want to display everything in the queue, you'd have a test which tests the type of the thing, the element in the queue.
Conventional
and then, depending
style.
on whether it's a doctor, it would call the display doctor routine. If it's a nurse, it would call the display nurse routine, and so on. You would be unlikely to have a window in waiting for a door, but you might have code in the system that did that as well. And as you build up a large system this way, you'll have at first 10 and soon 100 versions of this kind of code scattered around the system. And it becomes a nightmare to maintain. It's also harder to build because you just have the sheer bulk of all that code to write. It's harder to modify because you have to maintain consistency. If you go and change one thing, you've got to change all those places where it occurred. It's also harder to understand because if you come into a system that's built this way, you can't see the forest for the trees. You're just confronted with a mountain of irrelevant detail. And the example here is if you wanted to add janitors now to this simulation, you'd have to go back and fix up all those places, which would be a chore, and that's assuming that you found all the places that you needed to fix up, and you get bugs and inconsistencies in that regard. So there's a principle at work here, which is that if any part of a system depends on the internals of another part, then complexity increases as the square of the size of the system. In other words, in each of these places, we've got a piece of code that's getting bigger and bigger, not just because of what it does, but because the rest of the system is getting larger. And you can sort of see this graphically if you think of these little circles as the number of parts of the system, and the blue lines as the interactions between them. There get to be more and more blue lines until you get a forest that you simply can't deal with. This is truly a limitation to what you can humanly accomplish. There are a couple of approaches you can go from there. You can stick with simple problems. That's sort of the academic approach. Or then there's the industrial military approach, which is to mount enormous efforts. But there's actually a better way. In other words, the complexity you have is not so much intrinsic to the task you're trying to do. It results from the point of view you have about what you're doing. And it was the people who worked on Simula who first ran into this problem and saw a way to deal with these situations more simply. What they did was to sort of change from the procedural view, which is that in these procedures you have to do a dispatch on the types of the objects. And they flipped it around to the other point of view, which is the object-oriented one, which is that within every type of object you have all the procedures that work on it. And so in addressing an object, you need to dispatch on the procedure you want to call. So if we go back and look at the situation we had before, it can be represented pretty much this way. You're testing on the type of the object that you're wanting to operate on, say print in the queue. You test if its type is A, then call A's version of print. If the type is B, then call B's version of print. And if the type is C, then call C's version of print. You can collapse that down into one more general statement, which is just to call X's type's version of print. And then you can still simplify that some more if you see this as addressing X and asking to have something done as sending the message print to the object and letting the object do it itself however it wants to. And if you go even farther, if you decide that you're going to do everything in your language this way, then you don't need to have this sort of send to circumlocution. And you can just write X print or X operate, whatever. So let me take a minute and just describe how Smalltalk does this. Smalltalk gives you a syntax for both simple operations, such as asking for something's size, or printing an object, where you would just say a size. That would send the message size to the object A and return some value. There's also an arithmetic form of this, and here's a compound statement, a size plus 5. This would be accomplished by sending the message size to the object A, taking the resulting value that comes back and sending the message plus 5 to that. And then for larger procedure calls, if you will, that have several parameters, you can comprise a message in the following way. This reads as a plus 5 between 0 and q top. That would be evaluated by sending the message plus 5 to A, getting some result, and that result would be sent the message between and with two parameters, 0 and the top limit, q top. And this syntax with the keywords and with putting the receiver at the beginning reads a little bit like English. And if you look at something like a music system that's been built in this way, you find statements that read very naturally as kind of a micro-language having to do with music. For instance, this statement, instrument, play this note for that duration. So for a little bit of terminology, we have objects, and they're described by classes. That just sort of factors the description of what the objects consist of and what they're capable of doing. Then we have messages, which are being sent, and we call the part of the name of the message the selector, and the message is the selector plus whatever values are being passed along. And finally, we have methods. These reside in the classes, and they are the specific code for how to carry out the request implied by the message. Now, to see how this works in just a simple kind of object, we'll consider how you'd model XY coordinate pairs, which in Smalltalk would be called a class point. The first thing in the class describes what fields are in a point, namely there's an X coordinate and a Y coordinate. These are local variables in each instance of a point. And here is a brief excerpt from all the messages that are understood by points and the code that is invoked, the methods that are invoked if sent that message. So this first one is X colon Y colon, which allows you to store into the variables inside of the point with a new X and Y coordinate. If you send a point the message X, then it will return its X value. If you send it the message Y, it will return its Y value. If you send it the message plus and another point, then it will create a new point, sending new to the class point, which will make up a new one, a blank one, and initialize it with an X coordinate, which is this point's X, plus the other point's X, and a Y coordinate, which is this point's Y, plus the other point's Y. So this is just a short way of doing sort of vector addition of these two coordinate pairs. And this last message down here would divide a point by a certain scalar value. Creates a new point and whose X coordinate is divided by n from this one, and whose Y coordinate is scaled down by n as well. Having made this description, we can now build up rectangles from these points. Here's a model for a rectangle, which has two fields in each object. It's a point describing its top left corner and a point describing its bottom right corner. And there would be a couple of messages in this class, top left to return the top left corner, bottom right to return the bottom right corner. And now you can see how the capabilities that we gave to points allow you to do interesting things very simply. For instance, you can ask for the center of this rectangle, for which there's no stored value. And it will invoke this method here, which says return the top left plus the bottom right divided by 2. And those messages will invoke the similar code back in class point to return a point whose coordinate is the arithmetic mean of these 2 points, which will in fact be the center of that rectangle. So we're building up a little sort of a graphical micro-language here. It's really just a set of procedures, but they can be described very tersely in this manner. Now let me just show you how this works inside the machine, as it were. The rectangle is a little piece of storage, and it has a pointer to its class. And it's in the class that the information is stored about what fields it has. It says it's got a top left and a bottom right. And these names correspond to the slots in every little rectangle, which is a piece of storage. There's also a pointer here from the class to an object called a method dictionary, and it correlates the names of the messages being sent, the selectors, with the code, with the methods for returning the appropriate values. So here's top left, and there's the method that says return top left. Here's an entry in the dictionary under the name center, and it points off to the method that we just examined for calculating the center. And these structures are put together recursively, so the point for the top left points to another Smalltalk object. This one is an instance of class point, so it would point off to some description of class point in its first field, and that would tell you that this is the x and the y. And this other point is just the same way, except it has different values for its x and y. Now, having put all those things together, it's now possible to produce considerably complex simulations without running into the problems we had by mixing different similar interacting data types. But there's still some problems. When you want to go describe a new class of data, you have to write the whole thing from scratch. And also, you'll find many places where there's the same kind of code. For instance, if you're talking about collections, you might have arrays, and you might have character strings, and you might have dictionaries, and you'll have similar code for doing, say, selecting all the elements for which such and such is true. You'll have to have copies of that code in all those classes. So once again, you're into a problem of you can build more complex system, but once again, you start running into one of these limits of just how complicated things are. And the way for dealing with these problems is, again, to try to simplify and yet make things more general. And the concept we have to take advantage of here is inheritance. Inheritance is very simply put into the implementation I showed you by having a chain that goes from a class up to another class from which it will inherit behavior. That way, if you send a message to this object, and it's not found in the method table for this class, then it will go and look in its superclass and see if there's a definition for that message here. And this continues on up all the way to a sort of a default superclass, which describes the general properties of all objects. Now, what the inheritance allows you to do is to save a lot of code. Here's an example of factorial. And here's a simple description for how if you send the message factorial to an integer, then it says, am I less than or equal to 1? And if that's true, then return the result 1. If it's false, then return myself minus 1's factorial multiplied by myself. So this is a recursive definition of factorial. Now notice that it's defined for integers. And here, integers inherit the properties of all objects. And these might be simple things about how to print themselves. But the properties defined in integer are inherited both by small integers, which may be compact and have particularly fast operations, and also by large integers, which may have a greatly extended range of values. So if you ask to compute the factorial of 20 or something, it will go through this calculation. Let me just show you how this inheritance works. Both of these classes here will inherit from class integer. Now what's interesting is when you actually invoke this code, running something like factorial of 20, there will come a time These will start out being small integers because 20 is a small integer. But there will come a time when the factorial of the number that's smaller will actually be a large integer. And we have here an asterisk implying multiplication. In most programming languages, most conventional programming languages, it has to be known what the types of the integers are on both sides. But because that is simply a message, it's just the name of an operation, this code will work regardless of whether the receiver is a small integer or a large integer, or some completely different kind of integer that you defined. So there's a kind of a symbiosis between the inheritance that's available in the system and the polymorphism, in other words, the ability to work with any different types that's inherent in the sending of messages. And what this does is it makes code much more reusable. It means that you can have generic code throughout the system in some superclass that can be used by all of the subclasses. And it greatly factors the code in your system. You can then add messages to subclasses or override them. For instance, here's an object called a pin that might have some little program in it to draw a line for a certain distance and then turn a certain angle for doing some geometric design. You could define a subclass of that called a commander, which would do all the same things, but which might actually own a whole set of pins itself, so that when it was told to draw a line of a certain length, it would tell all of its sub-parts to draw lines of different lengths. And you could make really fun designs that way. And then you could define another class below that called a collider, which would do a kaleidoscopic type of pattern. And the only thing you'd have to do would be to override the turn operation so that the sub-pins would turn opposite directions for every other pin, and you get a kaleidoscope effect. And all of this is done without having to write any new code in the subclasses except for what's different. And you can also make use of the code that you've overridden. For instance, in initializing this commander, it can invoke the initialize code that's inherited by its parent by saying super initialize. This is kind of a pseudo variable. It's like sending the message to itself, but using the definitions inherited from above. And then it can put in its own particular code as well that it wants to be done for initialization. So in this case, it would initialize itself normally, and this fan-out operation would be one which would take all the sub-pins. Instead of all starting in the same direction, it would spread them all out. Another point that I'd like to bring up that I think of as a part of object-oriented programming, although it's probably not a strict requirement, but it certainly is a complexity issue, is automatic storage management. If a system doesn't have automatic storage management, it inevitably has all sorts of code sprinkled throughout it dealing with the lifetime of storage. And it's code that's it's easy to get the code wrong, so it's hard to do it properly. It doesn't tell you anything about the problem that's being solved. So in that sense, it's irrelevant detail. And if it's wrong, it will cause the system to crash most terribly. So I just think that if we're going to talk about what it means to be object-oriented, I think we have to assume that the language is high level to begin with, and I think of automatic storage management as being a requirement for any high-level language. I'd like to talk just a little bit about the operating system interface, which is another area that's important in object-oriented programming languages. Because if you try to bolt object-oriented semantics onto a conventional operating system, you can have problems at the interface that really detract from the overall value of having an object-oriented programming language. And I think what you need to do is to have the point of view that the operating system itself is just a collection of objects. And there are all sorts of objects like files and directories that this kind of programming is perfect for modeling. It's good for modeling the display. And then the one thing that the operating system gives you is a certain number of primitive operations, which presumably are either necessary to get at the hardware or that run particularly fast. And what you have to do is to be very careful in how those are interfaced to the rest of the programming language so that all the requirements of the operating system are met when you finally call it. And if there's a failure, for instance, if you call some operating system routine for turning a rectangle black that requires integer coordinates on the rectangle, you better be sure that you have just integers by the time you do that. But you don't want to reflect that requirement out into the whole programming system. You want rectangles to be able to have floating point coordinates and fractional coordinates. So what you have to do is to check that on the way in and use the object-oriented protocol to find out the integer coordinate, pass that on to the operating system. And that way, you can get the result you want without having made things ungainly for the programmer. I have sort of a simple test which I consider how you find out if a system is truly object-oriented. And it's, can you define your own new kind of number, for instance, a fraction? And you'll have to define how the plus operation works and how the less than comparison works and all that good stuff. But once you've done that, can you use one of your numbers in a rectangle that's a part of some program that you're writing to do graphics, and then tell the operating system to blacken that rectangle and have it all work? And what it requires is that all of the operations that want to get done are done by sending messages, and moreover that you can add your own new kinds of messages and have them work. And the key to this is that you need uniform reference. In other words, everything is an object. And the only way you can do anything is by sending a message to an object. And what this guarantees is a property which I call simulation, which is if you only have a hold of this object by a reference and you can only send it messages, then you're sort of guaranteed that somebody else can come along and put a completely different kind of object out there, and everything that you've written will work because you don't know anything about it. All you know is what kinds of questions it can answer properly. Now, people ask, is object-oriented programming just good for graphics? The answer is no. It turns out that graphics is a great application for object-oriented programming. And the reason is that graphics consists of a whole family, kind of an algebra, of similarly behaving objects. For instance, there are atomic objects or primitive ones like points and lines, text and bitmaps. And then there are higher level objects like rectangles or ovals or polygons that are made up of smaller objects. And then there are really complicated, or at least really high level ones, such as overlays. You might have an overlay and it overlays 50 different other polygons, or a window which represents a clipped representation of some graphics. But these all will obey the same message protocol. And you can put them all in a hierarchy and they'll all inherit the same properties. So it's a domain which just factors itself out very nicely this way. And it's interesting that the application of graphics is one where that has in the press has been called object-oriented when you talk about graphical user interfaces. And I think that's just because the kind of operations that you do with the screen are very much like the operations you do inside of a real object-oriented programming system. There are lots of other tasks for which object-oriented programming is effective. For instance, building compilers. If you look at compiler construction as a task where you're generating a tree that corresponds to the parse of some linguistic statement, you can model that tree perfectly that way. You can have a node that represents an expression, a node that represents a method, a node that represents a message. And the compiler simply builds this tree, and then each node will have local properties, local methods for generating its own kind of code. And that's how you would generate code for something you're compiling. Or it can have code for printing back source code that corresponds to it, and you can use that to do a pretty print of some code in the system. It can also have methods in it for locating the PC. And if every node in your tree has a way to locate where the program counter is in it, then you can find the program counter in a large method. And you can use this then in the debugger. You can also have other methods for printing the structure that you've compiled into another language, and that way build a translator. So that's another area that just breaks down perfectly this way. And there are many others, airline reservation systems, banking systems, all can be factored nicely this way. There's a couple of neat things that were done in the Smalltalk system just by virtue of making things into objects. For instance, Smalltalk has an object called a context, which is it's like an active object that corresponds to stack frames as the language itself is running. And if you can actually send messages to these stack frames, then you can take the frozen state of a computation held onto by the debugger, and in perfectly high-level language code, go through and single-step your program or read out temporary variables. And it makes the writing of a debugger a much simpler problem than in a language in which you can't do that. One last thing I think is worth mentioning is in a true object-oriented system, if you send a message to an object which isn't understood, then it will go through the inheritance hierarchy trying to find a meaning for that message that you sent. And ultimately, it will terminate at the end of that tree without any definition. And that is typically an error. Now, what's usually done is that there's, or at least what's done in the Smalltalk system, is there's a way of catching that situation and turning it around so that if you've sent some message, foo, to an object, and it isn't understood anywhere in the inheritance hierarchy, then the system itself, the interpreter or whatever you've got, turns it around and bundles that message up, the name foo, as an object called a message, and presents it to the original receiver of the message as the argument of a message that is message not understood. In other words, when everything else has failed, the original object will receive a message that says, I didn't understand this message, and its name was foo. And it will also have these arguments if it had arguments. And at that point, then, up in class object, there can be code for when a message is not understood that invokes the debugger. So that's how you handle simple errors of a message being sent that isn't understood. But there are other more powerful things you can do. For instance, if you have a file that's not open, for which it wouldn't make any sense to respond to most messages, you can change it into a kind of object that doesn't understand those messages. And then when those messages are sent, it has a chance to discover that, reopen itself, change itself into a proper file, and then do the operation and carry on. Or an even more powerful use of this would be you can have objects in the system which aren't even in your computer. They might be on somebody else's computer over a communication network. And if you send a message to them, they get a chance to look at the message, see what it is, and they might actually cause the telephone to be dialed and a message to be sent over the phone, the response come back, and then respond. So this is really all a manifestation of what I said, the simulation property. As long as you have this very tight control over how things can be accessed, objects can simulate all sorts of behavior. Well, thanks. That concludes most of the major issues about object-oriented programming and several of the details of the Smalltalk system. I'll next be talking with Dave Ungar about some of the questions that people ask most frequently about object-oriented programming.
Well, Dan, after that nice, clear explanation of object-oriented programming, it sounds like just the thing to use for building these complicated systems. But I think a lot of people are going to be afraid of the efficiency of it. What do you think about that?
I don't think of it as a big issue. obviously, because I've been using it for the last 15 years. But it's a reasonable question to ask. My first thought about it is machines are always going to run faster and faster, and somewhere in there it makes sense to go with the language that works best and let the hardware take care of the speed. It's still an interesting question to ask, why is it slower and how much slower does it have to be? And there's certainly a lot of great energy that's been applied to making message sending go fast. It used to, the Smalltalk system used to be, I think, 200 times slower than other things comparable. And most of the decent implementations now run between 10 and 5 times slower than something like C. And so I don't see that as a big problem. People say that automatic storage management takes a long time, but it's something like 10%, and I think in your scavenging, you're like down around 3% of the time. And plus, there's another factor in there, which is if you don't have it, you have to have explicit code in there. At least if it's written into the language, then it all happens in the most optimum possible way in a decent implementation. So I think it's just that, the future is more efficient, and it's the question of when you want to reap the fruits, and I think now is the right time.
Well, I certainly agree. Now, some researchers, in an attempt to make things go faster or to just simplify their lives, have left certain things out, or even in an attempt to come up with new languages. So, for instance, there are a lot of ingredients in what you talked about. There were abstract data types, there were classes, message passing, blocks, inheritance, and one thing you didn't mention, which were type declarations. So of the ones that were in there in Smalltalk, which ones do you think were really essential? And also, what would you feel about type declarations, which was one feature that's not in Smalltalk?
Boy, okay, you mean, the thing that I think is most essential is message sending, because that's what gives you this interface that ensures that you can simulate. And that's what all the real power comes from.
So that's the thing that hides how an object does something from how you ask it to do something.
From the request of what to do to the implementation of how to do it. That's right.
I see.
And now, I think inheritance is also really important because inheritance is, together with the polymorphism, gives you the reusability. And that's what's making object-oriented programming so successful. Now, I don't think that classes are essential, and you must feel the same way because you've done this language self that's based on prototypes.
Sure.
And you get all the same advantages. It's just a different view of the world.
Sure, and some more flexibility. Now, something in both Self and Smalltalk is that everything is an object, whereas one of the easy roads to efficiency is when you have simple things not be objects. What do you think about that sort of path?
Well, I think that gets you into problems. This example that I gave of being able to define your own class of numbers, use them in the existing class of rectangles, and having the operating system blacken a rectangle, I don't think will work if you have that kind of a situation. In other words, if you have numbers and rectangles that are built into the system as primitive objects, it won't work.
So it's not only that message passing is essential to have, it's essential to have for every kind of data in the system.
That's right. Yep.
I see. Well, there are other features in Smalltalk, and I guess Self, that are not in some of these other languages, like blocks, for example. Is there some connection between blocks and the object-oriented programming?
Well, blocks, I didn't say anything about blocks, but blocks are where they're like Lisp lambda expressions, sort of. They're where you can pass a piece of code along as a parameter of a message. And then blocks are like any other objects. They understand messages, and the most common ones are to evaluate yourself. What it lets you do, having an object-oriented framework lets you have blocks behave that way. And having blocks that behave that way lets you write your own program, your own control structures, which is very nice. So you can take a piece of code that say, gives you a little block that gives you the population of a city, and then you can take a collection of cities and ask it to collect up the populations of all of those. And it's very simple.
So that extends the power of objects to hide complexity by letting them even hide the way control works for certain situations.
That's right. And yes, to hide it and also to give you control structures that are appropriate to the various universes you're implementing. That's right. Mm-hmm.
Okay. Well, what's the relationship between abstract data types and object-oriented programming then? I guess if you take away inheritance, do you just have abstract data types, or could you connect this up to some of that work a little bit?
Well, let's see. A lot of languages that give you abstract data types don't really give you true polymorphism, and I think that's the difference.
I see. So it's really the message passing with the dynamically determined polymorphism.
That's right. Yep.
Okay. Well, I guess type declarations were one thing which we're going to talk about.
Yep. Smalltalk does not have any type declarations, nor does self. There isn't any reason that there can't be type declarations, I think. But it's a different situation. Conventional, strongly typed languages type according to what I would call concrete type. And in an object-oriented language, you can still assert type declarations, but what you want to assert is what I would call the abstract type. In other words, you want to assert that this is an object which understands the following protocol. And then, if you do that, it gives you the same kind of security that people like to feel about code they've written, which is that you've asserted that all these things are so, and therefore the code shouldn't break for that reason. I think there's still a philosophical dispute over whether that solves the whole problem. You know, have you nailed down every possible leak if you have declared the type? And obviously that's not so, because you can have values that are out of range and all this other stuff.
So people who like writing type declarations would have to get used to writing more abstract declarations than they do now.
That's right, but I don't think it would be any problem. I actually did a type system once with Alan Borning for Smalltalk. It didn't turn out to be sound, but we did get a chance to use it, and it felt completely natural. And it added the kind of readability. People say that it makes code more readable because you know kind of what you can expect. And I think that's true to a certain extent.
Well, let's see, in the minute or two we have left, how about warning people off? There must be some situations where it's bad to use object-oriented programming, and perhaps in the interest of responsibility, we should just mention what those are before the tape ends.
Well, I don't think you'd want to pave your driveway with it. No, there are certain things for which it's not good. Object-oriented programming is a style of imperative programming. So in my opinion, it's the best way to do imperative programming. If you consider something like rule-based programming, you would not use Smalltalk to do that. You could build a rule-based rule-based programming system in Smalltalk or in Self, but the programming you would do using it would be a different style of programming.
I see. Well, what about the people who are coupling, say, logic programming and object-oriented programming?
I think that makes a lot of sense. So, in other words, what they will do is where they need imperative statements in their logic programs, they'll use an object-oriented programming language. And I think that's appropriate. I also think that whenever possible to get by with just one language, you're that much simpler off. You're that much better off because things are more learnable and there's, things are simpler. But at the same time, if you've got to talk about things two different ways, you better get appropriate languages for each.
Well, thanks very much.
Thanks, Dave.
So this chart up on the right here, a lot of the last part of that talk was, what about this feature, and what about this feature, and what about this feature? And a kind of subtext of that was C++ had just come out and was sort of paraded as the big new object-oriented language of the future, and they're pointing out that C++ isn't actually object-oriented at all. It doesn't have first-class procedures. It doesn't have the uniform reference that he was talking about, where everything is an object. And it didn't have automatic storage allocation. So our object-oriented system, well, Smalltalk, of course, is yes, yes, yes. The object-oriented system we're using this week, obviously it has Lambda, it has automatic storage management. It does not have everything as an object. So in our system, numbers, for example, are just numbers, and it's only the abstract types that are objects. And that whole business about can you use a rational number in the coordinates of a point in a rectangle addresses that if you think of numbers as not being objects, then you can't invent exact rational numbers and have them fit in with everything. So how is industry stacking up? So the next improvement on C++ was Java. Everything is not an object. Numbers aren't, the same as in our system. What they do have is a parallel set of object classes that are named after numeric types, but those classes can't do arithmetic. So it's like you can have numbers that aren't objects, or you can have numbers that can't do arithmetic. It's a big mess. A big, big, big improvement in Java is that it does have automatic memory management, and that eliminates a big class of bugs. And does it have Lambda? Well, it has something called anonymous classes, which got shoehorned in about the third or fourth revision of the standard, that you can kind of use as lambdas if you really stand on your head, but it's not designed in. So this is sort of where things stood as of, when I started giving this talk 25 years ago. Since then, there's JavaScript, a language with a terrible name because it has nothing to do with Java and is in fact better than Java. Does have Lambda, does have automatic storage management. What does kind of mean? Okay, you can treat things as objects, but sometimes they act funny. Okay? It's making progress. Ruby, which is another not so widely used because it's better, but real-world industrial language is a yes, yes, yes. And they're even talking about now putting Lambda into C++ in its latest revision. So this is all good news, actually. It means that good ideas do eventually kind of filter down into industry. So we're not totally wasting our time here at the universities. On the other hand, these languages are fairly hideous, and it's not just because they have bad designers that they're hideous. It's because they kind of try to do, they're based on every good idea at once. So when you program in Scheme, the big organizing idea of Scheme is first-class procedures. And every problem that comes up is done in a way that fits into that framework. So it has a very uniform syntax, and it has a pretty simple semantics. Simple not in the sense that it's intuitive necessarily, but in the sense that there aren't very many rules. Smalltalk, which you saw some examples of in this talk, is very, very different from Scheme in its notation and its ideas and everything, but it has the same simplicity. In Smalltalk, everything is done by sending messages to objects. And that means, again, a very simple set of rules and great generality. In industrial languages, so far, they haven't been brave enough. Instead, what they've done is said, well, this is a good idea, this is a good idea, this is a good idea, and they try to cram them all into one. Eventually, maybe they'll even learn that lesson. Okay, see you next week.